All right, let's go through this one. What is the output of the program below? So we have increment is some function, takes an integer x, and it says x plus plus, and that's the only thing that's inside of it. The main makes a counter variable, passes counter to increment, passes counter to increment, and then cout's counter. This question is basically checking to make sure you understand that we're passing by value and not passing by reference. So this will actually output just plain old 0, because the value that we pass into increment is not the same one that's going to be in our main. So this is one value in memory. Then we copy by value into increment, because this is passed by integer, not by passed by reference. Short. And we get 0. So again, we're passing in, we're passing in increment, we're passing into increment counter. Yes, it'll still function with a void main. It's one of these strange things. Why is void main accepted in C++? I'm sure there's some like real reason. This one says what's wrong with it. Difference between void main. There's no real difference. For some reason, both of them seem to compile in both at least GCC and in MSVC. You'll notice that when I put my code, I usually use int main void, explicitly saying I'm not taking anything from command line here. You should always return some integer. I think it's kind of strange not to, but it is technically valid for the main method not to have an integer return. Okay, so the following C++ code is described best as, so we have void counting sort integer pointer items int count. So I'm looking at this, I'm like, okay, I can already see that there's a semicolon here, so bam, I know the answer is going to be function declaration. Why is it a function declaration and not a function definition? A definition would be, we'd have the braces here. So if we had this, we have, here is our function declaration. If I want to actually have the function definition, I would do something like this. Now we open up the braces, so this is actually a definition. So I'll be like, I don't know, it takes an integer pointer, an integer count, return, count, plus equals, I don't know, item. Sure. Wait, what am I supposed to be returning? Oh, void, nothing. Oh, we can't even return anything. Fine, cout this then. There. And I'll just say plus items. No, plus 7. There. Some stupid function. This is the definition of it. Yes, I feel like function is going to be the new way of saying function for a while. So again, this is a declaration. You can tell it's a declaration because it has a semicolon here, and it doesn't have any parts of the body. This is our actual definition of our method, or of our function. And it includes some body and actually does whatever it was that you asked it to. So if we think of card, for example, here's card.h from lab 9. And most of these look like they were commented out. So here's lab 9's card. This is card.h. You can see that most of these are declarations, and some of these are declarations and definition. So for example, inline, and return something, so this both declares and defines it right at once. However, this portion right here, which is the constructor, is just the declaration. When we go to our card.cpp, I wonder why I had this commented out. Whoops. Oh, how did I just accidentally make everything lowercase? Rip. Don't know how I did that. Fixed. There. So here's are all the definitions of whichever function we are. So we have toCharSuit, and that was declared here, and we actually defined it inside of the CPP. Okay, what must the expression, C++ expression B, and then the little arrow thingy, C mean? So usually when we see something like this, it means that B is a pointer to something, and we're dereferencing it to get some member variable of C. So the answer to this one is going to be B. So decrement B by 1 and compare it to C. No, there's no minus minus here. There's no 1. There's nothing like that. Substitute object B by object C. No. You can have an assignment operator, which would be an equals, which would be similar to this one. And does not compile. No, this is valid C++ code. So we're looking for dereference B and get member C. Okay, so assuming PTR points to one dynamically allocated rect object, I'm assuming is a rectangle object, how should we destruct this object and free the memory? So for this we have, are we deleting an array of something? No, we're not. So therefore, this one is incorrect. It doesn't say dynamically allocated array of rectangle objects. It just says dynamically allocated rectangle object. So we can automatically say we're not deleting an array, so we don't need to worry about this one. This one probably won't compile because it'll depend on what you're asking your compiler to do. Technically, you can call this, here I'll make a rectangle. So if I have some class rect, public, I don't know, int x, rect x is, I don't know, equal to 7, sure. Alright, so here's my destructor. How did they have this? Oh, pointer. So they're saying rect pointer is equal to new rect, and we're just going to pass nothing in this case. Then we're going to say cout. Actually, we don't need to cout because we already did that. Pointer. I think they're calling it like this. Okay. So, does this actually work? Let's find out. I'm hoping that MSVC is me. Of course it does. So, as far as I'm concerned, this shouldn't compile. You should never be calling the destructor directly like this. The whole point is to have something like the delete keyword for a reason. So if I do this afterwards, I should get either, if I control F5, it's going to... Oh, interesting. Oh, I don't have anything dynamically or allocated. It doesn't actually break. RIP! I never really understood why you would use rect x. You wouldn't usually. Like, you would have a getter for this. So if I have something like x, I would say like, I don't know, int get x. Oops. Return x. And then I would actually return my x variable. It's at 144p. Is anyone else lagging? Like, the stream says that it's uploading fine. I can turn off my torrents, I suppose. Oh, my torrents aren't uploading, so that shouldn't be an issue. No, I'm sitting at uploading at 6,700 kilobytes per second. So I think that's on you, bruh. Sorry. So the reason this is not giving us a double deletion is because, again, x is on the stack anyway, so it doesn't really matter. We're not deleting something twice in heap. So the answer they're going to be looking for is actually delete pointer. Pointer equals null does not do the same thing. That just moves it and says point to some other thing. Upload torrents. However, this is valid C++ code, and apparently does at least compile in MSVC. I could, I guess, bust open bash and see if it compiles in what? What is this thing called? Lab 9? CD Lab 9. CD Lab 9. There it is. Okay. G++ standard equals C++11 main.cpp. There's nothing else in here that I need, right? Nope. Dash O some main. That's friggin' 0. RIP. Right, CRT debug is from MSCVC. Let's just take this and go. Standard lib should be okay, but I'll do it just in case. Also a Windows only thing. There we go. Okay, so G++ doesn't complain either. I suspect if I say dash pedantic. Wow. That's actually kind of depressing. Huh. Alright, so I would suggest that what I would actually do here is, I guess I would, if I had this question, I would accept both answers. However, you should never actually do this. Like, the whole point of having a destructor and having the delete is so that you never actually have to call the destructor directly. You should just call it by deleting it with the delete keyword. But apparently it's valid enough that pedantic G++ didn't decide to say that it's not valid. It's kind of annoying. Executing the following C++ code sequence. We have a list of integer pointers, which is a pointer called C1 is equal to new list with an integer pointer of 5. List integer pointer C2 is equal to some new list of integer pointers 10. C1 insert 1 new int 5. C2 insert new insert C1 remove 1. So, does this cause a memory leak? The answer, according to last year, was that it doesn't. However, that is just blatantly false. Here, oh my gosh, that does not copy very well. Enter, enter, enter. Okay, so here we have that code exactly. And we're going to get rid of our rectangle class for now. Oops, I just accidentally built it without the debugger. RIP. I have my flags. There we go. There we go. See? Detected memory leaks. Bam, 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 bam. Memory leaks everywhere. There's memory leaks everywhere. So, again, question 5 from last year, the answer was false. However, that's incorrect. The answer should be true. I'm assuming his explanation of why this didn't cause a memory leak was he had executing the following C++ code. So maybe he thinks that, like, just the C++ code, there might be something later. But if that's the case, then there's not enough information to answer the question correctly. So I would never ask something like this, where it's, unless I said something like executing the following C++ code, and this is only the code that's in the main method. So I made explicit that this is the only code in the main method. Then I would ask something like this and say, yes, it does cause a memory leak. But if I said something like this is not the only code in the main method, then you don't know whether or not it causes a memory leak. So either way, false is never the answer. So this question is just silly. Oh, what does this code actually do? It inserts into position 1 some new integer, and then in position 2, it takes whatever is removed from C1 and places that into C2. So we're going to end up with some 5 into C2. Why does it cause a memory leak? Oh, because we have the new keyword right here. So we create this list on the heap. So unless we call delete on those particular guys, they're going to still be there. So if I go, you can see here we have all these memories that are leaked out. But if I go and say delete C1, delete C2, let's see what we get now. We still get one memory leak. Why is that? Well, our list is using a t-pointer. Oh, that's the iterator. A t-pointer, which means that we're putting something inside of our array that's inside of the list that we also dynamically allocated. So we no longer have a way to actually call delete because our list is pretty naive, and the destructor of it just literally says delete the container. It doesn't say loop through everything inside of our container and delete it. If I wanted the memory leak to be completely gone, I would have to say for int I is equal to 0, I less than size I plus plus delete m underscore container at whatever the position is. And so the whole idea was that you would actually delete what's at that position in your list. Oops. Let's not break the list for later. Is that open? Alright, so suppose that ARR is an array, thanks, but does that create a list of 5 pointers, or the first value in the list is 5? No, so remember from the list constructor, it takes a capacity. So it makes a list of size 5 by default. And then we place the first value as integer of 5. So suppose that ARR is an array of pointers to card objects and that ARR has been allocated dynamically. Executing this statement will release all memory used by ARR and the card objects that it points at. So this is kind of a weird question. So the answer is false. And I'm suspecting what they're looking at is that, oh, you didn't actually delete the card objects. However, it doesn't say that the card objects themselves have been stored dynamically. So this is one of the questions where I would say there's really not necessarily enough information to answer it correctly. But in general, if you have a question like this and you're thinking this is dynamically allocated, and the cards may or may not be dynamically allocated, then you should say that it's false. It does not necessarily release all of the memory used by ARR. If class Y is derived from class X, then instances of class Y inherit functions from class X. It's a pretty straightforward inheritance question. If Y is derived from X, then yes, it inherits everything from X, assuming that it has access to see it. It inherits it regardless, it just may or may not be able to call it. So this is going to be true. An example of a last in, first out data structure, we have list, stack, and queue. A last in, first out data structure is a stack. So in this case, the answer is just B. List is, it's not last in, first out. It's not a first in, first out. It's just a linear data structure. And queue is a first in, first out data structure. So here we have executing the C++ code sequence stack of ints. It's a pointer a equals a new stack of ints that's of size 30, and stack int b30 a equals b. Does this give a compiler error? Does it compile with crash? Does it compile and runs and causes a memory leak? Does it compile and run normally? So this compiles and runs but causes a memory leak. Why? Because we didn't actually delete the stack. Yeah, exactly. That's why I don't like this question. Like, it's not clear whether or not it's an array of pointers on the stack, each pointing to an object on the heap, or whether or not it's an array that was declared on the heap that's pointing to an array of pointers on the heap. It's completely ambiguous. Here's another example, here's this question that claims this is a memory leak, but yet earlier we have this one, which is clearly a memory leak, and this is says false, was not a memory leak. So again, 5 is wrong. The answer should be true, that is a memory leak. This one is correct. It compiles and runs, but does cause a memory leak. It's just interesting that within the same exam, there's competing and differing information. Not sure how that really got past them. I know that's why that's why a lot of them have been changed. Okay, so the C++ statement int pointer a is equal to new int dynamically allocates an array that can hold 7 integer values. If we call delete a, if we call delete a on this one, then yes, it's no longer a memory leak. So this does not make an array of size 7. No, it's not completely new. There are ones where I've changed the wording of it, where they're actually kind of similar. Like, there are some good questions on this exam that test stuff that I think is relevant, but there is a lot of questions that are just very poorly worded, or the answer is incorrect, or similarly. So the C++ statement int pointer a equals new int 7 does not allocate an array that can hold 7 integers. What it does is it allocates a new integer with the value of 7. So how do you tell the difference? One uses parentheses, these little guys here, and the other one uses the square brackets. So if we had an integer pointer like so, like int pointer, I don't know, a equals new int 7, then this says, let's make an integer array of size 7. But this one says, let's make a new integer that has the value of 7. The size of a vector is determined at compile time. This is false. A vector is not determined at compile time. It's determined entirely by runtime. So because a vector can shrink and grow, we can't possibly know what the size of it is going to be at compile time. Can I zoom in my visuals? Oh, good call. Oh, that's probably too far. Till this updates. Oh my gosh. YouTube thing, why are you so slow? There it goes. Oh yeah, that was really hard to see. Sorry. Somebody should have said something earlier. What is the difference between compile and runtime? Okay. Here's an example. This causes no compilation errors. None. If I compile this, no problems. However, it's a memory leak, so it causes a runtime error. Something happened at the time of running the actual program that crashed it. Or, in this case, dumped memory somewhere. So it doesn't necessarily always crash it. C++ templates are where was I? Yes, I think I was on question 12. C++ templates are instantiated. Templates are non-instantiated, as needed during compilation, as needed while the program is running, every time they are called, and for all built-in types. So the answer to this one is as needed during compilation. So templates have to be instantiated. If there was no instantiation of the templates, then your code just would simply not run. As needed while the program is running is false because the code actually needs to have existed beforehand. It needs to know how to make an ordered list of integers. It needs to know how to make an ordered list of characters. Every time they are called, not sure what he's saying with that. Every time they are called as in what? When it's running, as in when it's compiling? Like, that's completely ambiguous. For all built-in types, again, kind of, that's just like, doesn't mean anything in reference to this question. So these two don't even make sense, which only leaves you with 3 possible answers, and the answer is going to be as needed during compilation. So what happens is, let's say we have ordered list, and right now, we have an ordered list of integers. And now we have an ordered list of doubles. And now we have one of characters. So we have ordered list of A, we have ordered list of B, we have ordered list of, or we have ordered list A, we have ordered list B, and we have ordered list C. This one is of integers, this one is of doubles, and this one is of characters. So what actually happens is when I go and compile this, like let's say I do this, I hit the Windows local debugger, compiles on my code, and then runs it. Nothing's output, so there's nothing there. No memory leaks, yay. So what actually happens is the compiler sees this ordered list and sees that it has some template. So it goes to ordered list, and everywhere that it finds this class T, which is the first parameter of the template, it replaces it with integer. So you get this whole thing that you have of code replaced all with integer, and that's placed on top of your executable file. Then it's continuing its compilation. It's like, oh, I found ordered list again, but it's of double. Do I have ordered list of double in my symbol table? It doesn't. So it goes back to the ordered list header, takes this T, and everywhere that it finds it, it replaces it with double. So all the way through the entire header. So now it has two, one of integers and one of doubles. Then it hits this third one, and it says, oh, here's another ordered list. It's of characters. Do I have an ordered list that is of characters already inside my executable? No, I do not. So it goes back to the ordered list header, takes this T, replaces it with character all the way through the entire header, and instantiates that on top of your executable file. So when you're done, and you've actually compiled everything together, there's actually 3 ordered lists on your executable, and each of these would be of ordered list something, of whatever type that is. Would polymorphism cause it to be C, like ordered list parent class C? I might have to explain that a little better. So you're saying as needed while the program is running. So like you're saying if I had like ordered list of some parent class, D? It's called D. Because like I can do this. Okay, so now we got 2 classes, some parent class and some filthy child. Filthy child's default constructor calls some parent class's default constructor. And so if I say order list of some parent class of D, then I run this, I get I am the parent a whole bunch of times. Why? Because order list uses list, which makes a container. So it just makes a new array. And when you call something with the array, so this one is going to be some parent class, it actually does this. It calls the default constructor for each one of those in the ordered list. If I have filthy child, then I get I'm the parent, I'm a child, I'm a parent, I'm a child, I'm the parent, I'm a child, a whole bunch of times. Whatever the default size of the list is, which is 20. Oh, 200 apparently. Let's make that a little bit more reasonable. There, now we actually get it only 20 times, not 200 times. I believe that's Merry Christmas, you filthy animal, but I'll accept it. Okay, so the main advantages of a doubly linked list, this should have the word list, over a singly linked list are the following. Can traverse backwards as well. This is a huge advantage. If you remember from what I posted for my code on assignment 2, and you saw how I actually moved through, where is it? Okay, I'm going to make this smaller so I can actually find my own code. Add head, no one cares about that. Add, here we go. Okay, so my add in my assignment 2, I check to see if we're some default case, call add head. If we're not some default case, check to see if whatever the I is greater than or equal to the size divided by 2. Then I know that I'm closer to the end of my list, so why am I going to loop from the start of my list? I actually start from my tail and loop backwards. Otherwise, I'm closer to the start of my list, so I start from my head and loop forwards. So that's one advantage to a doubly linked list over a singly linked list. It needs less memory. That is false. A doubly linked list for sure needs at least a node to have a next pointer. So we already know that it must take up, a previous pointer. So we already know that it must take up more memory because we have at least one more pointer of memory for every node that's stored in our doubly linked list. By default, pointers are size of word, and word on most modern computers is going to be 32 bits unless you're explicitly compiling for 64. Insertion is more natural. It 100% is more natural. Let's say I do something like, where's an example inside of here? If you remember from our singly linked list, insert tail or add tail looks kind of gross. But add tail for our circularly doubly linked list is just basically the inverse of whatever add head was. So we start at the, did my Visual Studio, okay, thank you, computer. For a second I thought my Visual Studio froze. So here we start the tail, we get its next, and we can actually set the new nodes next equal to the head, and the previous equal to what the current tail is. Then we do 2 more changes, one to the head's previous and one to the tail, and we're done. So in here we don't actually have to loop all the way to the front of it, whereas if we had lab 9, add tail. No, that's not a good one. I don't want to add the tail. No. Where's the add? Here we go. So here we're have to looping all the way through to get to the last, whereas before I could actually insert closer to where I was. I can't do the little hacky thing and check if I'm closer to the tail or closer to the head because I can only start from the head and loop forward anyway, so there's no point of actually doing that. Yes, hash tables are significantly more natural, but you guys will not learn hash tables until next term, I think. I think you guys learn it in SE 2205, which is the course that Kevin Brightwell is teaching. That's really nice. If you're wondering which data structures are used in real life, all of these are used in some way, shape, or form. It just depends on what you're actually doing. If you look at something like kernel code for an operating system, the only 3 things you're ever going to see are, or I shouldn't say ever, 90% of the time, the only 3 things you're ever going to see are a hash table, an array, or an intrusive list. An intrusive list is a linked list that's flipped inside out. So instead of the node containing the data is actually contain the nodes. Alright. The class linked list is derived from an array-based class of list. This is not true. And luckily, you have the headers that are already given to you. So if I asked you this question on the final, you should very easily just be able to go and look at the headers of linked list and be like, oh, hey, it doesn't inherit from anything. Therefore, this is blatantly false. Linked list is not derived from an array-based class list because an array-based class list uses an array. A linked list is nodes being linked to other nodes. So one uses an underlying array of whatever type you want it to hold. The other uses an underlying bunch of nodes linked to each other to hold the data inside of the nodes themselves. Okay, how do we release all the memory allocated below? We have int num students is 93, string pointer names is equal to some new string array of number of students. We don't know anything else about it. We know that so far we've just made an array of strings. We haven't put any strings on them dynamically. We haven't put any strings on them anywhere else. So to delete the following, all we have to do is delete array, because it's an array of strings, names, and then we're finished. Suppose that a class X contains a public instance method with the declaration prototype of the following: integer function, character pointer string, and integer pointer k, const. So the const indicates which of the following. Executing the function, will not change the values of parameters str and k. So this is false. If we wanted that, we would have to put const in front of this. So we would say character const str, const character str, or const int this guy, k. The value returned by calls to the function is always the same. Well, that would be a really stupid function. Why would you ever be calling it if you could always return the same value? Why wouldn't you just literally put the value where you needed it to be? 3. Executing the function will not change the values pointed to by str and k. Okay, okay, I can sort of see what he's going to. He's saying because they're pointers, you're not changing the pointers themselves versus what they're actually pointing to. Fine. That's also false because the const is not on the pointers themselves. Lastly, executing the function will not change the values of the instance variables of the object against which it is called. This is correct. It is not. This allows us to be like, let's say this is inside of list, then we know that fn cannot change anything about our list. And if you remember from our linked list, we have size is const, because size just returns us an integer. IsEmpty is const, because IsEmpty just returns us a boolean. Retrieve head is const, because we're just getting something. We're not actually removing anything. Same with retrieve tail, same with retrieve, and same with get head. So, the call frame at the top of the call stack is associated with the most recently called function that has not yet finished executing. This is true. The call stack starts with having nothing on it. When your program begins, the main is pushed on top of it. The return of the main returns some integer, for example, to the operating system, and it tells the it knows where back on the operating system it's supposed to go. Do you absolutely need that const there? No, of course not. If you wanted to change something about your object, you would just not have const here. What was I saying? Oh, so the call stack is going to start at the bottom, and we put main on top of it. So main's call frame is always at the bottom of your stack. Every time we call a function, we place another call frame on top of whatever that was. So here, let's get rid of the filter child. Let's make some function foo that returns 7. And I don't know, int foo2 return 8. I don't know, int foo3 return 9. Foo2 foo3. Oh, I wonder if I can do, let's do something more interesting. Int A, int B, turn foo2 of B, turn foo of A, int Z. Okay, so now we have 3. Yeah, you guys need something, so this foo3 of foo2 of foo 7. There we go. Okay, so foo3 is passing foo2, which passes foo. So foo3 gets executed first, so that is placed on top of our call frame. What does foo3 do? It returns foo2 of b. So it's going to say, okay, what am I doing? So foo3 is like, first I need to find out what my parameter is. So it goes and checks, oh, I'm going to call foo2. Then foo2 is placed on top of the call stack. Then it says, I need to figure out what my parameter is. What's its parameter? Oh, it's a call to foo. So foo is placed on top of the call stack. Then finally, this 7 is passed in. So foo is on the call stack. It's popped off. Then foo is placed back onto the call stack for here, for the return. It's popped off. Foo2 is like, I'm done here. I've returned my value. So foo3 is like, oh, I have my parameter finally. It was all of this. It executes, hits this return foo2. Foo2 is placed back onto the call stack. Foo2 does the same thing with foo again, places foo back onto the call stack. Foo executes, gets popped off of the call stack. Foo2 gets returned to, it gets popped off of the call stack. Foo3 gets returned to. Foo2 says, oh, I'm done. Foo3, here you go, here's the value. And Foo3 is like, all right, I'm done. Pop back off the call stack, and now we're back in main. Finally, main says, oh, there's nothing left that I have to do, so it returns 0, pops itself off, and the operating system says, oh, I'm finished, and goes back to whatever it was doing beforehand. So, if we wanted this to be simpler, we can go 3 separate functions, 8, that don't take anything. So now we have foo3, foo2, and foo. So foo still takes some integer, and the other twos don't. So foo3 just returns 7, yeah. So foo3 is going to say, okay, I'm going to push myself on top of the call stack. So now we have main. So our call stack right now is going to be main, and above that, it's going to have foo3. Foo3 says return 9, so that's now popped off the call stack. Comes back to main, it sees foo2, so it places foo2 onto the call stack. And now it's like, what does foo2 do? It goes, returns 8. Foo2 says, okay, I'm finished, so it gets popped off the call stack. Main continues. It says, oh, I found foo, so it pushes foo onto the call stack. It goes and finds foo. Foo just returns 7. When that's finished executing, foo gets popped off the call stack. Now our call stack is just main. We hit return 0. Main says, oh, I'm finished. Pops itself off the call stack, and the operating system continues where we are. Or wherever we were, I should say. Okay. The following C++ code sequence: stack, integer pointer, pointer C1 equals new stack, integer pointer of size 5. Dynamic array of integer pointers C2 of size 3. C1 push new int, that's a value 10. C21 pop. So, yes. So when it gets called, it puts itself on the stack, and when it returns, it gets popped off. So this question is also a little silly because, for example, let's say I have this. Here's our little thingy. What is this, C2? Okay. Oh my gosh. DAC copy and paste from PDF dough. Thank you. Okay. So we don't have a dynamic array, so we're going to change this to, I don't know, Q. Yeah, it doesn't have one of those. It's a Q that doesn't take anything. So now we have, what the heck is this? It's like C2 at 1, we can't do that. Wait, what has something that actually does this? Let's just do an array. Oh, we can do a vector actually. Do I have vector included? Nope. Right. Okay, so now it says, here we have C2 of 1 equals pop. And it's like, oh, the correct answer is will not compile, except you don't know anything about this. It doesn't say only the following C++ code. So perhaps I have something over here that's like int, I don't know, pop return 7. Oh, look at that. Now my code actually does something and compiles. So, a silly question. What was he looking for? He was looking for something to say will not compile, but you don't know this at all. The idea is that, oh, pop is just free floating here, not attached to this stack, so he was looking for something like c1.pop, which is also valid, other than we'd have to do this because it's a pointer. And now it's going to be like, well, I can't guarantee this because this is an integer pointer, so this would have to be an integer. New int. Yeah. Anyways, the point is that he was expecting you to realize that we're not popping something onto C2 from C1. But the issue is that there could be some function called pop. It doesn't say only the following C++ code. It just says the following C++ code sequence. So you have no idea whether or not there's something called pop. The call frame corresponding to main is always at the top of the call stack. This is false. It is always at the bottom of the call stack. Always. If you make your program run like this, there's only one thing on the call stack, and that is main. It's on the bottom of the call stack. There's nothing else that can happen before main. Main is the entry point of your program. So the operating system starts your program on main. So stack will always start at main. Assume that class stack uses member variable mcontainer of class list. Then class stack extends class list. No, this is false. That's called aggregation. The easy way to tell the difference between inheritance and aggregation is an is-a versus a has-a. Inheritance is an is-a relationship. Aggregation or composition is a has-a relationship. She would say a person has a car, but a person, hopefully, has a right hand. That's both aggregation or composition. A person is, hopefully, a mammal, and that would be inheritance. So all persons are mammals, and persons have a something. They have a hand, or they have a car, or they have a something else. So the has-a is composition or aggregation, and the is-a is inheritance. What's the difference between aggregation and composition? I don't think I asked you about that because I think that how did I do that? Because I think that actually having a difference between them is kind of silly. So I don't ask you about it at all. I think it was defined. Where was it here? Where was I? 20-something? Right. I think it was originally defined as saying aggregation includes something and I actually don't think there's any difference. There should not be any difference. I'm hoping I took it out. Please tell me I took it out. Where would it be in? Inheritance? More classes? Aggregation and composition, okay. Aggregation, Jordan. Spell things correctly. Wait, is that the only place? How is that possible? Constant, static, yada yada. Static members, friends. Member-wise assignment. Copy constructors. What the? Comments on the program. Where the heck? Did we even talk about it at all? Here's the move constructors. Oh, Nicole's saying something. Yeah, I actually can't think of an example of how that would be used either. Oh, there's a part 2. This one? Oh yeah, operating. An object of one class owns an object of another. Oh, that's right. Yeah, I've always used them interchangeably. I guess the way that we were taught it is that composition is a more specific version of aggregation. But like 99.9% of the time, people just refer to it as the same thing. Yeah, that would make sense. Yeah, composition is just a stronger way of aggregation. So you may have a struct that's inside of there, but it may not always be existing. So I'm assuming that's aggregation. But if the composition is a strong form of aggregation, so that basically, as long as the object that you're using exists, then its part exists, then that would be composition. The parts can exist on their own. Versus aggregation, where you're saying they can't. That's a silly... Oh, in aggregation they can. Oh, can't exist on their own. I see. I see. Yeah, that makes sense. So, like, a claw can't exist without a cat, but a car can exist without a person. So a claw would be an example of composition, and a car would be an example of composition or aggregation. I'm not going to test you on aggregation versus composition. Where was I? Was I on 22? 21? Right, I was just talking about extends the class list. Right. Here we are. Assume array-based list object declared as list integer pointer m5, and assume two additional declarations, int a3 and int pointer b equals new int of value 5. So line m.insert3 reference a will compile, line m.insert3 b will compile, and both lines in a and b will compile, or neither lines a or b will compile. Okay, well, it's integer pointer, so it's looking for an integer pointer. We're inserting at position 3, and we're inserting the reference of a. So that'll compile, because references are basically just pointers that can never have a null value. And b is an integer pointer itself. So this will also compile, because we're just passing an integer pointer in. So the answer to this one is both lines a and b will compile. Suppose that we have the declarations integer a3, pointer b. In a C++ program, the statement dereference b is equal to the dereference of a plus 5 is equivalent to the statement b equals a5. No, I will not be going through. I'd be going through like 8.5 million midterms if I was doing that, unfortunately. So I will not be going through the 1027 midterms. You're more than welcome to look at the end of the 1027 midterms to study for problem-solving type questions, but I will not be going over them explicitly. So this statement, dereference of b is equal to the dereference of a plus 5, is equivalent to the statement of b is equal to a at 5. No, this is false. A at 5 here, first of all, doesn't exist, so we're going way out of bounds. Dereference of b gives us the value of b, and that's equal to the dereference of a plus 5. So these are not the same thing. So let's put this actually into C++. Whoops, doesn't let me, thank you. Okay, so already it's like, hey, you can't do this because you're trying to pass me a type, I don't know if you guys can see this, hopefully it's a little zoomed in, but basically it says a value of type int cannot be assigned to an entity of type integer pointer. That's true. So I'm trying to say that there's some integer pointer b, and I'm trying to assign it to some value of a. Now if I do this, it's going to say that's totally fine. Why is mine return 0? Oh, forgot a semicolon. So this is the same. These are not the same. Either way, both of these are going out of bounds. So does this run? It breaks. Why? Because, well, apparently we went somewhere that's out of bounds, and we're not actually into places that we're allowed to touch. If I do, let's do something like this. then I get some random value. I didn't give it a random value. I actually just said, give me some position. This could be some huge number. And as long as I'm within, oh, that time I hit a memory location that I'm not allowed to touch, so I break. Let's try this one. 500? Okay, that's apparently still within where the operating system says, yeah, you can totally go and see what's there. So I get some random value that's inside of my computer somewhere. Here's another question. The C++ code sequence below causes a memory leak. Apparently, the answer to this is false. However, hopefully you can see there's this new keyword. Let's see what happens when we do this. We're going to debug it. Let's check out the output. Oh, there it is. Detected memory leaks right there. So the answer to this one from last year says false. The answer should be true. It most definitely causes a memory leak. The isFull function of a circular queue always returns false. This is false. This is kind of a weird question because you have to remember that this is not the linked circular queue. This is the circular queue with the array implementation. So the array implementation actually checks to make sure that it's not full. When it is full, it will call extend and extend itself further, but that doesn't mean that isFull always returns false. Sometimes it returns true. Correct. On our exam, I would say, if I was going to ask you for a memory leak, I would say only the following C++ code sequence. So I'm assuming like he's trying to be, last year he was trying to be sneaky, be like, oh, this is like kind of a tricky question because maybe there's a delete down here somewhere that you can't see. But like, why would you ask that? Like, you're not actually testing whether or not your students understand the information. You're just trying to be I don't know. I completely disagree with that way of teaching completely, because I don't think it's actually useful. I will ask you questions about memory leaks, but there's not going to be a whole bunch of just checking for new and deletes. It'll be similar to something like on the midterm, where it's like, we made these two new things, and it's an error question, and you have to identify, hey, that's actually a delete. Yeah, I actually was going to play League afterwards. How did this other guy get hired to teach? You're making the assumption that maybe I shouldn't say this is technically being streamed. Whatever. You're making the assumption that the administration of the university actually knows what they're doing. I would say that, like, the administration of the university has absolutely no idea what they're doing. They're constantly saying that we can't hire more TAs because, like, you already have too many, despite the fact that we don't have enough. And they get angry when instructors or professors get low ratings, but they continuously don't allow us to hire in people that are actually good at teaching. So you're going to get professors that are hired specifically only for research, and then they're told, oh, you have to go teach this course. And they're like, screw that. I don't actually want to go teach this course. So like, well, too bad. It's in your contract. So what are they going to do? They're going to go and they're going to teach it poorly, which I'm sure some of you guys have had before. Or you're going to get a situation like myself where we enjoy teaching, but we only get paid $6,000 for teaching the entire term, which makes it really hard to actually live on that. So either you get a situation where I'm actually going to eventually leave because I need to make money at some part, or you're going to have to hire us, like, actually for a livable wage. Most of us are pretty simple people. We don't need to be rich, but I mean, $6,000 a term is basically just ridiculous. What was I saying? Oh, inheritance models a has-a relationship. Inheritance is not a has-a relationship. Inheritance is an is-a relationship. So again, a person is a mammal, or so we hope, or a llama is a camelid. That's a better question. There is going to be one llama question on the final, by the way, and it has to do with inheritance. It's great. Now I'm very disappointed because I got a question wrong about that on trivia at grad club the other week. So yes, inheritance models a is-a relationship, not a has-a relationship. Static binding of functions is done at compile time, and dynamic binding is done at runtime. Anytime you see static and binding in the same sentence, you know that it actually happens at compile time, not that it happens anywhere else. Dynamic, and the word binding, means that it happens at runtime. So this one says static binding of functions happens is done at compile time, and dynamic is done at runtime. And you're like, this is true. Dynamic, run, we're good to go. Static, compile, we're good to go. What is binding? Binding just means that the value of something is actually bound there. So this usually pops up in casting. So if I'm casting something, and I'm saying, I want you to be a double. If I static cast, it actually checks to make sure it is a double at compilation time. If I dynamic cast, it says, you're not going to be able to tell whether or not this is a double until the program is running. Assume class B is derived from class A, and assume there are no virtual functions in either class A or class B. The following C++ code sequence, A pointer A equals new B, delete A, will do the following. Give compilation errors, compile but crashes, compile and runs but causes a memory leak, or no problems during compilation and runtime. Is runtime and execution time the same thing? Yes. Runtime and execution are usually just interchanged words. The answer, according to him, or according to last year, was will compile and run and cause a memory leak. But this is also just not true. There's not enough information given here how you can guarantee that this is going to cause a memory leak. So this one says, assume there are no virtual functions in either class. Okay, well, let's go and see what happens. Class A, and we'll say integer x, public A, x7. Forgot something somewhere. Nope, it just was slow. Class B, wait, do I have this set up the wrong direction? Class B is derived from A. Okay, we're good. Class B, A, we'll say public, sure, A, that way it gets everything. And it's got some integer y. And we're saying B, then A, whoops, yeah, A, nothing. What else do we have in here? B, and, what is it, Y of 7? Sure, let's do it this way. Okay, so this says that, exactly, it may or may not potentially cause a memory leak, but the thing is, the question says it does cause a memory leak. Full compile runs, but causes a memory leak. That's not necessarily true. If I have this, and I delete A, I missed something. Declaration, oh, because I didn't make it public because I'm stupid. We get no memory leaks at all. So let's go and actually change something. What if I take out the constructor of A? Calls it anyways, nothing. What if I say integer pointer x, and then I say, I don't know, x is equal to new int 7. And then I go and say the destructor of A is delete x. So now I have B, we're saying A is equal to new B, and A has this. Still no memory leak. Okay, well, what if I give y something? So here's B, and we're going to say y is now a new integer. Y is equal to new int of 8, sure. And we'll say the destructor of B, and we just go delete y. Make a mistake somewhere. Pointer to complete up. Oh, I forgot to make this a pointer. Okay, so here we have delete. Let's get rid of, I don't know, let's get rid of this delete x here. Aha, now we get 2 memory leaks, but what if we put the delete x back in? Now we just get one memory leak. So, we're actually having something that is having a memory leak, but only because we dynamically allocated something on ourselves. So if we get rid of this, so we have some B destructor, and we run this, we have no issues. As soon as we say delete Y, notice we didn't actually make Y somewhere. We still have no issues. As soon as we actually make a Y, oh, sorry, I say Y is equal to new int. I delete A here. Then we're not actually calling B's destructor, because we're calling the destructor on A, because we're saying it's an A pointer. So this never gets called, so the Y is never deleted. However, as you saw, you had to actually have dynamic stuff in a bunch of different places. I can actually get rid of this. Should still get a memory leak. Yep, one 4-byte long word. So here we have A, and B inherits from A, and it has its destructor, but we're actually only calling the destructor of A. There's no virtual methods in either of them. If I made this virtual, for example, then it would be fine. But if we don't actually have Y is equal to a new int, and we just have Y equals 7, then there's no memory leaks at all. Exactly. You would never be able to know that, which is why I would never ask you a question like this. This question is silly. As far as I'm concerned, you could have written A, B, C, or D. All of them could possibly be correct. On to more questions that I think the answer is wrong. A function must define a local structure variable to use with the return statement. If that was true, oh, I'm sure the prof next year will probably roast my exam somewhat, but probably not as badly as I roast the previous year. Everyone learns every single year. Things are going to get changed. However, I did ask Kevin Brightwell what he thought of the exam, and his response was, well, I can't tell you what one of the responses was because I'll have to announce that in class. One of the questions I should give a little bit more explanation on, especially for English second language students. And other than that, he thought that the exam was fine. So, since I actually trust his opinion, I'm going to assume that it's actually not bad. Oh, so here we're returning nothing. But this is not defined locally. We could have also done something like integer pointer, and we take in like integer pointer A, return A. Nothing was defined locally, but we returned something that was passed into us. So a local structure variable, I'm assuming maybe there was supposed to be some other words here, but this is not necessarily true. It may be true, but it could also be false. Vectors cannot be passed by value to functions. This is false. We can pass a vector by value. We just don't make it a pointer when we pass it. The program below will output the exact characters. Tower defense, product name, compiles but will probably crash or does not compile. The answer to this one is compiles but will probably crash at runtime. And I ran this in class. Oh, why is it false? Because it doesn't necessarily have to. Here's an example. I'm returning A. It's not defined locally. I mean, I guess you could argue that it's defined within the parameter locally. But it's not a local structure. It's just a very poorly written sentence. Like, It's just not. I'm assuming he means, okay, but even if you're passing this a back, it's the parameter version of it. But the way that C++ is actually going to do it is just a pointer anyways. So you're returning the local pointer, I guess, but it's local, but the pointer is not really defined here. It's defined in the actual creation of the call stack. It's arguable. It's just a very poorly written sentence. And the whole point is not to give you questions that are tricky and you must know like the ins and outs of the C++, guidebook or whatever. No one reads a C++ standard. Like, the thing's huge. Except for those people that make the compilers. Yeah, exactly. It's just a bad question. Okay, so this one I actually ran in class, and it will actually compile, but will probably crash at runtime. And the way you can tell this is returning a string reference. The string that we actually make happens inside of the function itself, which means that when the function returns, that string is deleted. So when we run it in main, we get cout product name. We have no idea where this is going to be. So when we ran this in class, it went for probably close to 30 seconds, which is kind of fun. We'll see how long it goes this time. Ah, not very long. So basically it's going to go until it touches memory that it's not allowed to, or it hits a null character, like an end of string character, which is usually just the null character. So here we don't get anything useful. Sometimes when you run this, there we go. That was more interesting. We get a whole bunch of stuff. What do we have? I don't know, sysmonth calculator, rebar window, tooltips class 32. So it'll just start dumping random memory. Why does it disappear? I'm not sure what you mean by disappear. Oh, yes. Because this is a string reference, and we're returning a reference to a local variable. If I did this, then we'll get tower defense. Oh, this thing's still running? Oh no, it ended, thank God. See, now we get tower defense. Because here, we're returning by value. So we're saying, here's a string, we defined it locally, returning it. The other one, we're saying return a string reference. But this string was not made on the heap. It's made on the stack. So then when this returns, it's deleted. So the stack is just empty there, and your program's like, okay, let's just go see what's in that memory location. And we just get a whole bunch of crap. This is kind of similar to why certain things where you overflow portions of your stack or you read from portions of your stack memory that you're not allowed to are usually very interesting security vulnerabilities, such as the Heartbleed bug was a really good one. Microsoft Server at one point in time did something silly where if they received the synchronize symbol or the synchronize command from a TCP connection, they would automatically make the space for the connection. But then people are like, oh, wait a second, I can do things like send a whole bunch of syn commands, but not actually ever acknowledge them. And so you could overflow the server and cause it to just start dumping random memory into its acknowledgement returns, which was kind of interesting. So if you guys want to see that, it's called syn flooding. And here it is. It works because you're just lucky enough a string ends when a string hits a null character. An integer is just 4 bytes. So you're always going to get 4 bytes. Now, since you made it, and it's still in the same location, then you luckily will get a 7. but it's not always necessarily true that you will get that. Where's the interesting one? IIS server sin what? I'll have to look it up later. Windows 2008 one. That sounds probably about right. It was a really interesting bug, though, to say the least. Oh, I accidentally just closed that rip. This one. Okay. Okay. We had one of these on the midterm. This is just a more complicated version of following the memory. So here we have some integer j is equal to 8. Some integer k, so far it doesn't have any value. Some integer pointer p, which is equal to a reference of k. So the easiest way to do these is actually write these things out beside. You can actually pay attention. This is, we have an integer pointer array. So array, or ARR I should say, is equal to some new integer pointer of size 4. Then we say dereference array and set that equal to the reference of j, which is 8. Then we say dereference p and set that equal to 4. So remember, p was equal to, the pointer p was equal to the reference of k. So k is now equal to 4. P is also pointing to the same location. Array at 1 is now equal to the reference of k. Array at 2 is now equal to some new integer 5. Array at 3 is now equal to some new integer 7. And then we see out dereference of array at 0, dereference of array at 1, dereference of array at 2, dereference of array at 3, and an end line. So the first question is going to be values printed out by the line labeled of 1 are the following. Alright, so dereference of array at 0. So where is array at 0? So we look around and we're like, well, here's array, and we're going to set it equal to some new integer 4. Oh, hey, we said array itself is equal to the reference of j. J is an 8. So we know that the first one's going to be an 8. So already, C is not the answer. Then we look to the next one. We say dereference of the array at position of 1. Okay. Oh, here's the position of 1. That's equal to the reference of k. So what is the reference of k going to be? Okay, well, k didn't have any value here, but we set p to it. Later, we set the dereference of p equal to 4. So what is this going to mean? This means that the dereference of p is going to be 4 as well, which means that when we have array at 1, which is equal to the reference of k, then this is going to be a 4. So the second one is going to be a 4. Next, we have dereference of array at 2. And so we say, okay, let's actually look at this. And we go back and we're like, dereference of array at 2. Oh, we set it equal to some new integer value of 5. So that's not bad. We actually know that this is a 5. Didn't have to follow anything crazy. Then we have dereference of array at position of 3, and we set that to a new integer of 7. So we know that it's a 7. We had 8, 4, 5, 7, so the answer is 8, 4, 5, 7, or B. Then we go and see what is the values printed at 2 going to be. So what happens after this? We say array at position of 0 is now equal to the dereference of array at position of 2. So now the value that's stored at the array of 0 is now equal to the value that's stored at array at 2. Then we say array at 1 is equal to array at 3. Remember, this is a pointer, so now we're just saying that pointer is equal to this other pointer. So they're pointing to the same thing. J is equal to 9. Then we say the dereference of P is equal to 6. So whatever P is pointing at, you're now equal to 6. Dereference of array at 0. Okay, so has array at 0 been changed? Well, array at 0 is equal to whatever the dereference of array at 2 is. What is the array at 2? It's equal to some new 5. So saying, okay, as long as this hasn't changed, we should be okay. Make sure there's nothing else over here. Array at 0 is equal to this. Array at 1 is equal to array at 3. j is equal to 9. Is there anything that's referencing j? Aha! The array is the dereference of j. So we dereference the array of 0, and we said it's equal to whatever this value was. But now we say j is equal to 9, but the start of the array was equal to j. And since we said j is equal to 9 down here, we know that 9 must be the first of the ones printed out. So the answer is going to be either 9657 or 9757. So already you can cancel out all of these ones. So now the only difference is the second one a 6 or is the second one a 7? So we go down here and we say, here's array at 1. So we're dereferencing array at position 1. Array at position 1 is equal to array at position 3. Well, what's array at position 3? A 7. Oh, okay. So we didn't change anything there? Nope. Then this is a 7. So we get 9, 7. Whoops. So we already know that this is the answer. But let's continue on and see what the rest is. Dereference of array at 2. So we didn't change anything array at 2 here. What was array of 2 before? It was a 5. So we know that it's going to be a 5. So we're going to get 9, 7, 5. And then you get something like, here's the dereference of array at 3. What has array at 3 been set to? It's not been set to anything here. It hasn't been set to anything here. It's a new integer up here that's a 7. We don't do anything else to it. It was never set to any of these references. So we know that it's still a 7. So the answer is 9757. I think you probably got asked a lot of questions like this in 1036, plus I asked one on the midterm. So as far as I can remember, I've cut all these questions out from the final. Actually, do you only have to dereference the art in the cost? What? Do you mean dereference the R in the C out? Do you mean? Yeah, autocorrect secured me. Okay, that's what I assumed. Okay, yes, because it is a double. It's a double pointer. Oh, right, I was going to check to see if I actually put that. Okay, if I open this, is it going to open on the left screen or the right screen? Thank God, it opened on the left, but we're only seeing the front of the exam. Screen cap was so ready. Okay, we're good. Okay, where was I? Oh, this question is just it's funny. It was talking about how much we hate portions of C++ with Kevin. Like, I actually don't mind virtual, but I hate things like static cast and dynamic cast and stuff like that. Do we have long questions on the final from 1027? You have long questions that are similar to the midterms of 1027. The final of 1027 tended to be more focused on binary search trees and recursion, not anything else. So here's an error question that's apparently worth 6 marks. That only has 2 errors. The errors that are pointed out on last year's final are that this public integer ID, or this integer ID should be public. Why? Because I'm assuming somewhere referring to it, this ID, that's okay. Vehicle ID, that's fine. This is an automobile ID. Right here. So, because we do this, we need to actually have it public as opposed to private. Where else is the error? I'm not seeing. Oh, interesting. Okay, so the other error is apparently that we need to have this is equal to 0. Where's the automobile with the... Oh, no, that's the automobile here. Why does it have to have a default constructor? We never call it with one. Okay, I disagree with that. So, apparently the other error is that you want to default this ID so that, no, deleting S causes an error because S and V. Yo, that's totally fine too, but, that wasn't pointed out as an error. The only errors that were pointed out was this equals 0, which I was trying to figure out why that was an error, and this not being in public. Is static cast automobile necessary? New car Chevrolet. No, you could have just casted automobile. You probably didn't need to cast it at all, to be honest, because everything in car has examples and everything else. Heck, let's copy paste this and see what happens. Oh, I think I have a version of this that's actually in a Word file, which is nicer to... Oh, I just opened the wrong one. It's our exam. No, I do not do negative marks. Negative marks is ridiculous. Not on something like this. Yeah, this question absolutely will not be on the final. Do I? Public vehicle. No, but that's okay. This one has a default. If I ever call automobile without... Oh, I do here because I static that may actually cause it. Interesting. That's a silly question. This is why I don't like things like static cast and private cast. I just think, like, actually understanding how all of this works just becomes kind of redundant. Inheritance is something you should definitely know. Remembering all the ridiculous types of casts that are inside of... This needs to be public. That are inside of C++ is kind of annoying. There, now it should run. It'll run. Let's see if he actually didn't catch any memory leaks. I didn't check that. No, it's good. Okay, we're good. Nope, you don't. You have it declared in the parent class. So here we have ID of 0. If I take out this ID of 0, we're getting this, which is like default argument is not at the end of the parameter list. So then we would have to say, okay, do this. Now neither of them have a default. So I guess he's saying it's an error simply because it's not at the end. It wasn't necessary for it to be there, so I don't agree with the wording of why it was an error. It said you have to have a default constructor. I said, well, you don't have to have a default constructor. But you do have to have a situation where it is at the end. There is one error question. I've completely scrapped this vehicle error question because it's kind of ridiculous. It's a more naturally flowing error question. So don't worry too much about this one, simply because it's a little bit too confusing, and I don't expect you guys to follow through with static casts and figure out exactly what's wrong with it. Oh. This, on the other hand, is a good question. This is a very nice error question. So what's wrong with this? Well, here's a struct point that's of a class. I would actually probably, if we use our exam, I'd change this to class. I don't like to just have structs and classes throwing everywhere. And it's templated with class T. So later we have void print point2, but it's not templated. We didn't pass it any type. So that's an error right there. Down here, in our main, we have point2. We didn't have any type here. So this is also an error, because there's nothing there. Those are the only two errors that you have, so therefore, it's worth 4 marks. This is kind of similar to the midterm one, actually, where we have some test class, and we say A, 10 and 14, and B, 20 and 30, integer pointer P, value, public test class int x, y, P is equal to some new integer, dereference of p is equal to x, which is whatever this value is passed in, and the value is equal to y. We set the values into x and y. Dereference of p is equal to x, so whatever we passed in, and this value is equal to y. Okay, that's fine. Then we print out dereference of p, the space, then the value, and then the end line. Alright, so we make a test class A, and we make a test class B, 1, 10, 14, 20, and 30. Then we said A is now equal to B. Okay, so is there a copy constructor? There's no copy constructor, which means it's implicitly going to call. No, I don't ask anything about structs. The only thing that really differs in structs in C++ compared to objects is that structs by default are public for all of their member variables versus private for classes. If I wanted to ask about structs, then we should be teaching C. Though I have seen some C++ programmers prefer structs for just piles of data, and I don't mind that. But for this class, since you guys have never done object-oriented programming before, I'd prefer to stick to classes. Also, next term, when you have SE2205, I think it is, with Kevin, then you're doing Java. There are no structs. Well, I don't think there's structs. If there are, I don't think anyone ever actually uses them. So everything's going to be classes. So you should get into the habit of having class in front of classes. Wait, you did structs in C#? Well, structs in C# are a little bit different, but usually you're using classes. I haven't used C# too much lately with any structs, so I don't remember off the top of my head. But what was I saying? Okay, A is equal to B. So we know this is going to call the copy constructor of whatever we have, some test class, and we didn't define one. So therefore, it's just going to dumbly copy over the values. So it's going to say test class A's p is equal to p and value is equal to value. So now we have a problem. This is why implicit copy constructors are not good. Now, A and B, their p points to the same value. So when we say set values 15 and 8, now both A and B, their p is pointing to the value of 15. So we say A.print, we're going to get 15 and 30. Then we say A.setValues 12, 10. So now we've changed this again. So now A and B are both pointing to 12 for their p. They have different values. And we say 10, B is equal to A. Okay, so B now dumbly copies itself back from where it dumbly copied itself from originally. So it copied itself over to A, and then later A changed something, and then it says, okay, now you copy me. So B says, okay, now my p is equal to A's p, and my value is equal to A's value. So when we say B.print, we had changed A to have its val of 10. So we know the second one's going to be 10. And we had changed the value to be 12, and they were both pointing to the same pointer at the time, so it's going to be 12, 10. So we're going to get 15, 30, 12, 10. Okay. So this is a question with outputs on inheritance. So we have animal, cat, and pussycat. And we make an animal, that's a new pussycat, and we say sprint and delete s and return 0. So animal, we have its default constructor is creating an animal. Its virtual destructor is deleting an animal. Its print is this is an animal with 2 new lines at the front and the end. Cat is creating a cat for the constructor, deleting a cat for the destructor. This is a cat for the print. Pussycat is creating a pussycat, deleting a pussycat. This is a pussycat. Notice that both of these are always surrounded by new line characters. I have no idea. Is it actually a type of cat? It's a band. This is the first official. What if we look up dictionary? What do you think the chance of it being in the dictionary is? A cat. Okay. That's so risky. Well, I did it on, what's this thing called? Edge? It's not Internet Explorer anymore. So I was hoping that it was going to actually, defaultly, hopefully not pull something up. That would not have been good to put on the stream. I believe I've changed this question. There's a similar question, but of course, who cares about cats? So mine's about llamas. So hint, hint, there's a question, but this one's actually about llamas, not about cats. So what actually happens here? We make a new pussycat, and we print it, and then we delete it. Okay, so the pussycat is going to call from the cat, who's going to call from the public. So it's going to say, call its parent's parent. So it's going to say creating an animal, and then it's going to say creating a cat, and then it's going to say creating a pussycat, and it prints, and it's going to say this is an animal, because we made an animal pointer, and this is not virtual. And then we're going to say deleting a pussycat when it gets deleted, deleting a cat, and deleting an animal in backwards order. I'm not using Microsoft Edge, I'm using Google Chrome, but I prefer Microsoft Edge to Adobe and or Foxit Reader, which is broken right now, for reading PDF files. Why are the constructors and destructors of cat called? Because they're all inheriting from each other. So pussycat inherits from cat, which inherits from animal. So pussycat's constructor calls its parent's constructor first, and then that's a cat, which calls its parent constructor first, which is an animal. So it's going to print out creating an animal first. That's the first constructor that's called. We always make our parents before we make ourselves. We always delete our parents last. So we delete ourselves, then we delete our parent, and then we delete our parent's parent if it exists. But when we're creating, we always create our parent, then create ourselves. If print an animal had virtual by it, then it's just going to say print out this is a pussycat. Why? Because this is virtual, and we have a situation where it's going to say, okay, look for the most specific version of the print. Yes, it would. Apparently we die first. Yep, if we were C++ objects. If delete was not virtual, would only the parent destructor be called? Oh, yeah, it would. Which is the issue that we were showing with the A and B earlier in the multiple choice. Whereas that's why he said explicitly there's no virtual functions. So you want it to be virtual so that you're making sure you actually override it for each of them. Okay. Here we have linked list. Do refer to the reference sheet for the definition of linked list. Okay. Linked list integer A, add head, add tail, add tail, add head, remove 1, retrieve head, remove 2, retrieve tail. Do we have similar questions on the final? To this one, yes, but it's not about animals, it's about llamas. To this one, I am not sure. I can't remember. What was I saying? Okay, so let's see what we do. We add 4 things in, 1, 2, 3, 4. They are going to be in the order of 1, 2, 3, and this is going to be a 4, so it's actually going to be 4, 1, 2, 3. And then we remove from 1, so that 4 is gone, and we retrieve head. Okay, well, now the one that we know is there is going to be the 1. So the first output is going to be 1. Then we remove the second position. Okay, so we still had 3 things left. Let's pull something up here, like Sublime. Much better. Okay, so we add head of 1, so we have 1. Then we say we're going to add tail, so we have 1, 2. Then we're going to add tail, 1, 2, 3. Then we're going to add head 4, so we add 4, 1, 2, 3. Then we remove 1. Okay, so we remove the first one, which is the same as removing the head, because remember lists start at a 1 index. So we have 1, 2, 3, and then we retrieve head. So when we retrieve head, the first one we're going to print out is this 1. Then we remove the second position, which is this 2. So we get 1, 3 being left, and then we retrieve the tail, which is 3. So the answer to this one is going to be 1, 3. This question? No. This question is not very similar to the types of code you will have to write. 38. I'm skipping 38 completely. I don't really think it's necessary to ask you to switch a procedural style implementation into a non-procedural style implementation. So there's nothing like this at all on our final, so we're just going to skip it completely. Okay. Write C++ code for a function find, which performs a linear search on items stored in a singly linked list, and returns the index of the first node that the search is successful. This line is missing a word. It should say returns the index of the first node where the search is successful, or that the search is successful with, and returns -1 otherwise. Note that index of node 1 and the index, that the index of head node is 1 and the index of tail node is size. Okay, you can assume that the functor is equal will be used for the class equality when the function find is called. Cool. Alright, so we have some class linked list, and all we need to do is start at the front and move through until we get to the end. And we're just going to continuously compare to see whether or not we had the same as whatever key we're trying to find. So how are we actually going to do this in code? Well, can you guys see this all right? Actually, I'll just pop it up in Visual Studio. What are we putting this in? Linked list. No, I'm going to write it in the main so it's cleaner. What do we get? Okay, so we're given this. And we have to write the rest. Alright, so we know that we need to start at the head. So we're probably going to make some node pointer cur that is equal to mhead. And we can do this because we're inside of linked list. Yes, there is a question very similar to this on the final. So now we need to know how far we need to loop. So we're going to say int k is equal to 1, and k is less than or equal to the size, and k++. So we start at the head, and we loop through until we find the size, or until we're still less than the size or equal to it, and we k++. Of course, we would want it to be whatever we find. Yeah, so I'll change mine to t. Like, I don't like item. You can call it whatever. I just always prefer t. This is like the standard way of doing it. So we know we're going to loop through, loop till we find where it's true. Alright, so it's going to be an if statement. If equality, whoops, it didn't give me the thing. Quality. Compare, because remember all of them have the compare at the end. This is from our standard functors. So all of these have some compare method. So we're going to compare. What are we going to compare? Alright, well, wherever we currently are, so cur's value. And we're just going to compare it to the key. If this is true, then we just return k. We actually return the place that we found it. If this is not true, then we just continue. So how do we do that? We just say cur is equal to cur is next. So the for loop just has an if statement, and this will return k, so it'll break out of it, Otherwise, it just moves current forward to the next node. If all of that goes through, and we didn't find anything, then there isn't one in there, so we return -1. So, again, if we're giving something like this on the exam, we already gave you this template portion. So you need to remember that, okay, I'm going to start at the head. I'm going to loop through until we're at the end of it. If I ever find one while I'm looping, I'm going to return it. Otherwise, I'm going to move myself forward. And lastly, if I finish my for loop and I never found anything, then I'm going to return a -1. Write C++ code for a member function add tail of a doubly linked list, class D linked list. You're not allowed to call function insert or any member function of the class D linked list. Okay, so let's grab this. So here's our here's what we're actually trying to implement here. So we need to know how we're going to add the tail. Okay, so we're going to make a new node. The new node, oops, what do we want to call this? Node. No. Insert node. No, that sounds silly. New tail. Yeah, that's better. Okay, we're going to set this equal to some new node that takes in the element, and that's it. Because the node should be overridden so that if we don't pass anything else, they default to null. However, we could have passed something to do with the previous or something to do with the next, depending on the order it is. Where was I? Right. So now we need to actually see whether or not we're going to input this. So if there is an mtail, so if mtail is not equal to null, then the tail next is going to be equal to our new node, so our new tail, and the current tails next, whoops, the current tails next previous, which is our new node, is going to be equal to our new tail. And lastly, we're going to say our new tail is equal to our current new node. Next. Oh, actually, we could just say new tail. Else, there wasn't anything there. So apparently we can't call add head according to last year, so we would actually say mhead is equal to new tail, and mtail is equal to mhead. And regardless, we're going to say msize plus plus. So again, if the, oh, this is not a keyword. Oh, it's because we can't call size. Well, that's silly, but I can call msize. If msize does not equal 0. There we go, much better. So if the msize is not equal 0, then the tails next is equal to our new tail, and the mtails next previous is equal to the mtail. So the mtails next here is the new tail, and its previous needs to be set to whatever currently is the tail. And then lastly, we set our tail equal to our new tail. If none of that's true, as in the size was 0 when we started this, then we just set the head and the tail equal to our new node. Delete this guy. Oh, this is a nice question. We're Write C++ code for a member function that reverses the order of items in a stack. For example, the item originally at the bottom should get to the top, and the item originally at the top should be at the bottom. You must create and use one temporary queue object to store items. You are not allowed to use arrays and vectors, or linked lists, or other stack objects as temporary containers for storing items. You can use any of the member functions of stack or queue to do this. So the container that the class stack uses does not matter here because you can implement this function solely using the member functions of stacks and queues. Cool. Okay. Here's our start here. So let's grab this guy here because I'm too lazy to type this out. So we know that we're actually within stack. So we have ourselves, which I guess is going to be our container. So what are we going to do? Well, we're going to loop while we're not empty. So while, I guess we can just say is empty is not true. Then we're going to take ourselves and say, oh, we need to make a new queue first. Queue of t queue. Yeah, it's fine. So queue dot enqueue. This, actually we can just say pop. So now we enqueue that. So after we've done this, we're empty. So everything that we had in ourselves is now on the queue. And now we just do the exact same thing. We just say while the queue dot is empty, not true. So while it's not empty, then we say push queue dot dequeue. And we're done. So we have queued, I don't know, ask Microsoft. I have just the whatever plus my router. I mean, the security is probably okay. I'm a little bit more lax than I need to be. So we make a queue. While it's not is empty, so this is ourselves. So we could make this a little bit more easy to see by saying this is empty or this pop, but it's not necessarily and this. You don't have to because it's going to find the push that's within ourselves. So while the stack is not empty, then we're going to queue onto our temporary queue whatever's on the top of the stack. Then once that's finished, everything that was on the stack is now in the queue. But remember, a queue is first in, first out. So whatever was taken off the stack first is now going to be the first one that's dequeued off the queue. So that'll be pushed to the bottom of the stack. And then the next one will be pushed to the second, and so on and so forth. And so what was on the bottom of the stack will now be placed on the top of the stack when we're finished this. Okay. The following question is about circularly double linked lists. Write C++ code for the copying constructor of doubly circularly linked lists. You are not allowed to invoke any member functions such as insert within your code. Also note that you don't have access to any iterator class. The complexity must be O(n). Okay, well that's easy. With respect to the number of calls to the assignment operator. Can we use push and pop whenever we want because the test includes standard functions? Standard functors? Or are they... Okay, so I'm very confused by that because first of all, push and pop are not in standard functors. So, but they are in stack. I have no idea why this has no big annotation question. That's why I changed it. I think it's a little silly to put this in there. This kind of gives it away that you're just looping forward. But yeah, you can use pop and push as long as we say you're allowed to use the stack and you're allowed to use their member variables. Or sorry, member functions. Ugh. Okay, so we're actually going to go and make a copy constructor. So let's copy this to start. Template class. T. Oh, it didn't give us the, oh, did they not give that on the exam? Oh, they didn't. So the first thing we need to know with a copy constructor is that we need to actually take the circular linked list. We need to take a constant reference to one of these. So we're going to say const, I don't know, other. So here's the guy, the first thing you need to do for your copy constructor. It takes the same type, it's a constant version of it, and it's a reference. So it's going to be other. Then we're going to say, all right, how are we actually going to copy over all of the data that's within currently ourselves over to the new one? All right, well, let's make a new no pointer. We're going to use this to move through things. So we'll say other dot head. Oops. So we have the head, and we're going to copy whatever is in the other one into ourselves. All right. So if the node is equal to null, should be null pointer. I'm bad at accidentally using null. Should never have to be. It doesn't have to be const per se, but that's just the signature of a copy constructor, because you don't want to actually change what you're copying from. That would kind of delete the or that would kind of defeat the purpose of actually doing this. So if the node is a null pointer, then it's empty. So we just have to say our head is equal to our tail, and that's equal to some null pointer. And then we just set our size equal to 0, and we're done. So this is basically the exact same thing as if we were having a constructor by default. Other.node, our other one's called other. So this is the other one's head. So otherwise, it wasn't empty, so we actually have to go and do some work. So let's say, make some new nodes. So our head is going to be equal to some tail, so our tail, and it's going to be equal to a new node. Where do we want to make? Oh, we already have the other's head, so we can just say, oh, we didn't even call this. What do I want to call this thing? Node. Oh, I used the name here, but I didn't call it node. Sure, let's call it node. New node, node's value. So we're going to say it, our head is equal to our tail, and all of that is equal to some new node that's made from this node's value. Oh, that should say equal to other.head. What does the const do before the other? It just means that we can't change this. So we can't change anything about other. We can call anything that's a const within them, but if we try and actually change anything, assign it to anything, it's going to break and not compile at all. So here we have our tail and our head. We're setting it to the first one, and we just have to copy the rest of the nodes. So we're going to say node is equal to nodes next. So we'll move one forward, and we'll take our size, and we'll plus plus. So we'll increase our size. Then we're just going to say for. Do we want a for loop here? What did they do last year? I can't remember how I did it in mine. Mine was not so silly. That's fine. So for, we don't have an initial value, and we say node does not equal copy.head. So we're saying, okay, our node currently, oh no, it's not copy, it's called other. Our node currently is pointing to the head of the other one. And we're going to move and continuously copy new nodes until our node equals the other's head. Once it has, then we'll actually stop and be like, oh, we've hit the other side of it, so we don't need to copy anything more. So what do we do for each of these? We say, well, each time we do this, we're just going to take our node and set it equal to our nodes next. So you can do it in a for loop like this, which is how they did it last year. You could also say while, what the heck am I calling it? Other.head node does not equal it, so node, whoops, node does not equal other head. There we go. Jeez, I can't even type today. Okay, so you can say this and then do a bunch of stuff and increase the node.next. So at the bottom we'd say node is equal to nodes next, and that's going to be the end. So each time before we move forward, what do we actually have to do? Just say mtail is equal to some new node. And we're going to take our node's value. So we're currently wherever we are. And we'll have to pass a null pointer because we also want to set our tail equal to our tail. So we're doing two things at once here. We're creating the new node, setting our tail equal to the new node, and we're setting what was previously our tail equal to the new node's previous. We haven't set the node's next yet because we don't know what that's going to be until we're done this line. So once we're done this line, we're like, okay, well now our tail, we need to add in its next. So we say its previous, previous is next. And so again, the easiest way to know where to move through this, if you can't remember, is to actually write it out on a piece of paper so you know which node you're looking at and you can visualize where you're moving. So we're going to say the mtail's previous next is equal to the mtail. So what is this actually doing? Okay, here's our tail and our previous next. So remember, our previous right now, here's our mtail, and our previous right now is going to be some mtail, which was the backwards. Wait, can you do double assignment like that? Oh yeah, that's totally fine. This is the same as just saying is equal to the new node. Enter. There. Whoops. There. That basically accomplishes the same thing. Okay, where was I? Okay, so the tail's previous next is equal to the tail. And so how do we know this is going to work? Okay, so we're setting the tail equal to a new node whose value is whatever node we're currently looking at, whose next is a null pointer, and whose previous is whatever the tail currently was. So this all happens before it gets assigned to the tail. So this node is what was before the tail, and now we have what was our new tail. So our new tail, its previous is now our old tail. So we go to the old tail, which is here, mtail's previous, and we ask, what's your next? Well, its next is going to be equal to whatever previously was in front of the tail, which would be the head. But that's not right. We need to set it to be our new tail. So we just say, your next is now our new tail. Then we need to increase our size. So m underscore size plus plus. And lastly, we're saying, okay, so we've copied out everything else. The only things we have left to do is make sure that we actually copy the head and the tail at the end. So we set our new head's previous to be equal to our tail, just to make sure that we caught that. And we say our tail next is equal to our head. So remember, we looped through. Is there one similar to question 42 on our exam? Yes, there's one very similar to this one. This is a very standard question because it's just like, it's going to be worth probably 10% of the exam. I think last year they had it worth 11 or something like that. Let me check. 11? Yeah. And so we're just checking to make sure, do you understand where a next and a previous is? This will be a lot easier for you guys because you actually did assignment 2 where you had a circularly double linked list, whereas last year I don't think they had one, at least not from what I saw for the assignment. And so I say, here's our doubly circularly linked list. Go make a copy constructor, go. So hint, hint, I may ask you something that's basically identical to this. It doesn't have to be this identical answer. There's lots of different ways you can do this. Again, you could set things like this null pointer. If you can do cheeky things like if you knew what the next was beforehand, you could set it there. You don't have to have this double equal sign thing. This has to happen, so this is basically just the first part. So you're going to make a new node. You're going to set it equal to the other's head. Then you're going to check to make sure that there's actually something in the other. Otherwise, you don't give a crap what's in the other, and you're just going to set all your variables to null or 0. You can also just say this is equal to 0, but it usually doesn't allow you to because it's not null. Then you're saying it wasn't empty, so we're going to make our head and our tail equal to the new node. Then we're going to call next on the node that we're currently looking at. And then we're going to say, well, it's not equal to the other's head. We're going to node next, set our tail equal to the node's value, our null pointer because we don't know what it is, and the tail. Set the tail previously to be pointing to the right place now. Increase our size, move our pointer forward, and finally change our head and our tail to be at the at the right position. Unique solution. Yeah, exactly. Define an operator overloading function which overloads array subscript operator as a member of d-circular linked list. Oh my gosh, that's disgusting. Okay, I would not. Don't get me wrong. I love operator overloading. That question is actually like kind of a little bit of a pain, unless they want you to use. Does it say anything about? It doesn't say I can't use something. I don't really like having the operator, the subscript operator, for a linked version of a list, simply because the subscript operator to me suggests that it's linear that I can access in O1 time. But with a linked list, I can't actually you can't actually access something in O1 time. It's going to be like ON. I wouldn't ask you something like this. I'm pretty sure I cut this one out. I didn't really like it. I didn't like having two questions on doubly circular linked lists. 43, draw an exact memory diagram representing the state of the program below. Okay. First thing is this is not a CPU. This is a program counter. So this should be PC, not CPU. Swap. Okay. Just swapping some stuff, take some samples, and where we are. Okay, so it's saying that we're at the return of swap. So what do they actually want for the memory diagram? What am I going to write this thing in? Alright, we're doing it. We're doing paint. It's happening. Alright, so we're going to have... Here's our program. Let's make a line. Okay, so the left side is going to be our stack, and the right side is going to be our heap. What do we have here? Okay, so here's where we are in memory. We're returning from here. Int num samples just randomly out in the open, so that's going to be some global variable. So, oops, that's not paint. If it's some global variable... Oh, good call. Let's just show the example. Yeah. Oh, yeah, theirs is much nicer. Alright, this is what they have as the answer. As opposed to me drawing it out very painstakingly. Yay! Oh, I don't know if I really like this global stretching across the memory, whatever. Will we lose marks for ugly drawings? Absolutely not. I didn't fail grade 8 art like Elliot, but that's actually a pretty good feat. I would put that on my resume. So here we have the call stack and the heap. So we know that on top of our call stack right now we have swap and main, because swap hasn't been popped off. We're currently here. So everything that existed within swap still exists within ourselves. So we see that it has some temporary 4. Why is temporary 4? Well, because we had swap being called here with samples at 0 and samples at 3. And so this was equal to the 4 that was popped in. Our temp is going to be equal to A, which we pass in here, so it's equal to 4. Oops. B and A point to some place in memory, which is in the heap, because we created them as new in the main method. And so we have 1, 3, 2, 4. Here's our samples. Our main doesn't have anything in it except for samples, so it just points to the heap. It actually should still have a program counter that says return address of operating system. But yeah, I'm not going to ask you to draw anything in class. This is simply a question they asked last year that's having to do with the stack and the heap. Alright, so that is all of the 2015 solutions.